talk is Dillies from Utah about generalized Boltzmann response.
Okay, good morning. So today I would like to talk about the generalized Boltzmann construction. So first I'll try to put the problem in context, then I'll present the construction, I'll give you the classification that we obtained, and then we'll see what happens when you try to look at mirror symmetry for the families we get. So our first application of interest are threefold which have mirror pairs, for which we can construct a mirror pair. And the first case that was not toric or complete intersection was used to Borgia independently by Voisin. And their construction relies on the existence of involutions on the product of the torus and a K2 surface. So actually their construction is very similar to what Varco and Witten did. And what Varco and Witten do is they take the product of three elliptic curves and they take a quotient that preserves the volume form on the product. So this model is actually very interesting in terms of physics, and the study was pioneered by Dixon, Harvey, Varco, Witten, and many more people have worked on this in fact. So this construction, since it's of interest, has been generalized by many people by taking more general actions on the tori. And since this family is kind of very neat and it's related to the construction of Borgia and Voisin, we have a natural question: can we also generalize the construction of Borgia and Voisin in the same way as was done for the tori? So let me first remind you how the Borgia-Voisin construction works. So the ingredients is basically a torus, so it is one curve, a K3, and some symmetry. Not any symmetry, not the kind of symmetry you see here on the picture. So more precisely, you have the torus with an involution. You get this for free. You always have the -1 symmetry, and then you take a K3 surface S with a non-symplectic involution. So what's a non-symplectic involution? Well, the action of the involution restricts to a character on the volume form, on the span of any volume form. And you don't want this action to be trivial. You want it to be minor density. That's what non-symplectic means. In general, it's not trivial when you look at the volume form. So it's something which is not very natural. So how do you construct a Borgia and Voisin threefold using these two ingredients? Well, you take the product of the elliptic curve with a K3, and you act simultaneously on the K3 and on the torus. So by doing this, what you do is you change sign of both components of the volume form on the product, and thus you preserve it. You can after this, you can take a mild resolution. It's in dimension 3, so there's no problem. You have your Calabi-Yau threefolds. So these threefolds are very nice because you can work out explicitly with them. There's a construction of mirrors. I'll come back to this later. And actually, Voisin also shows that the Yukawa coupling on both sides of the mirror actually agree, so it's nice. So how do we generalize this? Well, in a very natural way. This time we take two Calabi-Yau n-folds. In our case, they are going to be either curves or two surfaces, and they both have a non-symplectic automorphism of order J. I should say it's a primitive automorphism, meaning that the action on the volume form is of the same order as the action of the automorphism. But since P is prime, this is, you always get that. Then what do you do? Well, since you have this automorphism of prime order, you have an action on the volume form of the first Calabi-Yau, an action on the volume form of the second Calabi-Yau, and you look at the subgroup which preserve actually the product. So the same thing as what happened in the case of involution. So you take the kernel of this character, this is isomorphic to Z mod PD, I call this K, and then you do exactly the same. Take the product, you model by this subgroup that preserves the volume form, and you get the generalized Borgia-Voisin orbifold. Here it's an orbifold a priori because there is no reason that you have a perfect resolution, at least not when you have two surfaces. For threefolds, you're fine, but not for fourfolds. Yeah, so you have to pay attention, they're not smooth. So to study this thing, the main key is the orbifold cohomology formula of Chen and Rouen. So this is sometimes something that gets a bit messy because you have to look at all the conjugacy classes, all the possible fixed loci for each element of the group. But luckily, since here we're dealing with cyclic group of prime order, the formula really simplifies. What you're really interested in is the fixed locus of any element, gamma, since any element is a generator, and then you are only looking at the transit, so powers of that element, and see how it happens. So the real issue is to compute this shift here in cohomology. Since we are preserving the volume form, we have a finite group which is embedded as a subgroup of SO3, so this is going to be integer. So things are nice, but still computing this shift, actually the age, is actually difficult. So let me write down maybe what kappa is. So suppose you have a group element that you can linearize as e to the 2 pi I k1 e to the 2 pi I kn. Well, the age of g, or the shift, is just going to be the sum of these ki's. So, as we see, what you really need to do to understand the geometry of the quotient is to understand the fixed loci of g on the K3 and on the other canopy, which might be a curve or a K3. So we need a classification of non-symplectic automorphism on K3 surfaces, and luckily this exists. So a lot of people have been involved in this. And what's nice is that basically you characterize the action by only two invariants. The rank of the fixed lattice and the second cohomology, and the lattice which is fixed happens to be a P elementary lattice, and you just look at the order of the determinants. So for involution there's an extra condition, but not so important here. So this was very algebraic, but maybe let me make a little close. What we are having here is something very geometric. So let me just make a innuendo. So symplectic action. Surfaces. So as I said, the non-symplectic action is one which doesn't preserve volume form. So the volume form gets multiplied by some root of unity. Assume that P is 3. This gets multiplied by a third root of unity. So the question is, how do you study this? And actually, what's nice is that even though the object is not natural at all, the way it acts on the K3 surface is something very nice, and you see actually that if a K3 surface has such a symmetry, it's actually very rigid. So let me show you the general story. So in general, there's a bit more details, but let me focus on one case. And let's take the example of X, a K3, which is basically fibered over P1, and which has two star fibers. So if you look at the entire group of X, actually what you have is you have the following picture that appears. Sorry, so what's this? That's the gram graph associated to it. So the vertices correspond to classes in the Picard group of smooth rational curves. Okay? So since you know you have an action of a group of order 3, the first thing you notice is due to the general geometry of this graph, it can be a global symmetry. So you're not setting curves left and right. Okay? So each curve represented by a knot has to be preserved. So how does the thing act though? Okay? So since each curve is preserved, let's look, for example, at what happens around this level. So here you have a P1 with 3 P1 that intersect it. Clearly, these 3 points all to be fixed. Okay? There's no way to permute them around because there is no global symmetry around that point. But if you have a P1 with an automorphism that fixes 3 points, this automorphism has to be trivial. So you know already that this curve here is fixed. Same thing on this side. Can you say more? Well, actually yes, because look at this fixed point right here. And let's look at the linearization of zeta as the tangent space at A of the surface. So it's going to look like a matrix, and by Capstone you know that actually you can diagonalize this action. So we only need to find two non-trivial entries. What do we know? Well, we see that there is for sure one eigendirection which corresponds to the fixed curve, and this direction, the action is trivial, so you have a 1. And you also know that the action is non-symplectic. What does it mean? It means that on the volume form, you don't get the identity. So in other words, what it reflects on this level is that the determinant is non-trivial. So here, the only possibility is to have zeta. So what does it mean? It means that here I have an eigendirection corresponding to 1. Here an eigendirection corresponding to zeta. And now this is again a local story because you have a P1 with that 0 action which looks like multiplication by zeta. So I can induce that there is another fixed point, say infinity, where the action will be like zeta squared, etc., and you can propagate the action. So somehow it's very nice because when you have a non-symplectic action, somehow the story at one point tells you the story about the whole surface or triangles. Okay? So what do you get then in 3 dimensions? Well, in 3 dimensions you get an action on the product. So let me do a very dark. So suppose here now that you have your product. So this is your product of your K3 surface, and assume I'm dealing in dimension 3 times the elliptic curve. Okay. So you have a direction of the surface here, and here you have the direction of the curve. So if you look at the fixed point on the product, well, the action at A, call it Y, decomposes. Is there an A somewhere?
This place in the middle.
So in 3 dimensions we have a similar story as what we had in 2 dimensions. So the action decomposes into a block corresponding to the direction of the surface and a small block corresponding to the dimension of the curve. So here you know that what you have is a picture similar to what you had in this case. So I just erased it. And here you just have the action of the curve. So it's going to be either zeta or zeta squared. So an example of action you could have is zeta squared, zeta squared, zeta squared. How do you see it works? Well, if you restrict to the surface, you have indeed a non-symplectic action. The determinant is not trivial. Same thing on the curve, but if you look on the whole of the treacle, it preserves the volume form. So such a point is called a type 1, 3. So this corresponds actually to an isolated fixed point because there is no eigendirection associated to 1. So you could do the same at another point, assume that you have a fixed curve, then you know from the surface that the other entry has to be zeta 3, and in the direction of the elliptic curve has to be zeta 2 squared to preserve the total volume form. So again, it's a very local problem. So a big issue here is computing the age of the powers. Okay? So did people already study this kind of construction? Yes, there has been earlier work by, among others, Roth, who did the case P plus 3 dimension 3. And then there are some partial results in dimension 3 for P4, for dimension 4 and P2 by Borcha, Abe, and Sato. And also some partial results for higher P's in dimension 4 by Hulek and Singh. So what we get actually is a complete classification of all the cases. So I skipped here the pod numbers, which are pretty ugly. I just sort of give you a global overview by giving you the other characteristics. And what you see that the other characteristic is pretty ugly in the sense that it's pretty large. So only for automorphism of order 2 do you get small characteristic in absolute value. So I forgot to put the numbers, but for 3 you have about 60 topological families, and for 2, I don't remember this one. So for the Borcha-Voisin construction, there was a mirror pairing. That says the Borcha-Voisin triples, another Borcha-Voisin triples. So we have the same story here. Well, first let's recall how the mirror symmetry construction works in this case. Well, if you remember what I had written here, if you have a X, a K3 with the action of the non-symplectic automorphism zeta, the action of data is actually totally determined by the rank of the fixed lattice S equals R, and by A, which was the determinant basically of this same lattice. Okay? So Nicolin classified all K3s with a non-symplectic involution, and that's the picture he gets. And what's nice with this Christmas tree is you see directly that there is a natural obvious symmetry in his classification. And indeed, if you have a K3 with R some rank between 2 and 20, you can actually find a mirror just by taking R to be 20 minus R, preserving A, and there's another K3 in this family. And what's magic is that when you choose two mirror quote K3s and you do the Borchardt-Voisin construction, you get mirror Borchardt-Voisin threefolds. That's actually something which is pretty deep. So what do we have when P is bigger than 3? Well, when P is bigger than 3, I mean, it's beautiful, but mathematically it's not so nice because we lose a lot of symmetry. So I classified the different types of K3s depending on the order of the automorphism. And you see that, for example, for P is 11, you don't have anymore the reflection along some vertical axis. However, for P is equal to 3, so everything is red, P5 or P7, there still seems to be some hope that you will have a mirror family.
What was delta again?
Oh, delta I told you there was a third invariant to characterize these lattices for involutions. So it's either 0 or 1. That's the delta. So, do we have mirror construction? Well, we know for P equals 2 in dimension 3, it's true. For P equals 2 in dimension x equals to 4, that's also true. So Borchardt and Mate, actually, they checked this for the toric case, it's actually true all the time. So that's nice. What about when P is bigger than 2? Well, no like neither in dimension 3 nor in dimension 4. Okay? So there is no way to pair the new threefolds you get or fourfolds to another one in the family and get mirror pairs. So what's the problem? Well, in dimension 3, the main problem is you take higher order automorphism on an elliptic curve. So you look at these 2 points in the moduli, and what you see, well, these points are rigid. You cannot move them around and keep the symmetry. So there is no way to talk about a large complex structure. I mean, you're sort of fixed there. So somehow it was to be expected. In some families, you can also compute the Picard-Fuchs equation, and you see that the order of the equation is too low, so you don't have points with a maximally unipotent monotomy. So you see that you're doing it this way. So what about the dimension 4? Here, there is no a priori reason why you could not deform the complex structure. So what's the problem? Well, the problem is because of the singularity. As I mentioned earlier, the construction gives you a quotient which might not have a perfect solution. And to detect this problem, we use this criterion, the Dillies criteria. And what this criterion says is if you have a fixed point of a particular type, so I'm using the same notation as before. It's 1 over P, 2, P minus 1, 1, P minus 2, I mean, that's not very important. Then this does not admit a perfect resolution. Well, what's actually magic or unfortunate is that all the cases we have with P bigger than 2 have these kind of points. So none of this has a resolution. So this might be also one of the reasons why you might have to look outside this construction to find the mirror pairs. So what's next? Well, we would still like to construct the mirror pairs. So 2 options. The first one is to use toric geometry. So you could maybe hope to find toric construction where these involutions are compatible with the toric action, or maybe they might be in the form of a Landau-Ginzburg model. I know that Brunville and Wu have done something similar for Borchardt-Voisin type of constructions. So, but this will be for the future. Thank you.